6-sided dice rolled. Find each probability. First decide if they are mutually exclusive or not. So would the events of rolling a die the first time and then rolling a die the second time be, well, actually, never mind. That's independent, dependent. We'll talk about that later. So the probability that the number rolled is less than 3 or greater than 5. The question is, are those mutually exclusive? Yes, right? You can't have a number that's less than 3 and also greater than 5. So if they're mutually exclusive, we just literally add, because it says or, we add the probability of each occurring. So what's, if I have a die that is 1, 2, 3, 4, 5, 6, how many numbers there would be less than 3? 2 of them. So the first probability would be 2 out of 6, or you could reduce that to 1/3. How many of those are greater than 5? 1 out of the 6. So because they had the same denominator, you could have reduced or you could have kept them that way. 2 6 plus 1 6 is 3 6, which is 1/2. Second question says the probability of rolling a number greater than 4 or even. So is a number greater than 4 or even mutually exclusive? No, they are not mutually exclusive. You can have a number that is greater than 4 and even, right? So this time we're going to do the probability that it's greater than 4 plus the probability that it's even minus the probability that is both greater than 4 and even. So what's the probability that it's greater than 4? 2 out of 6, or 1/3 if you reduce it. If it's even, how many numbers would be even on that die? 3 out of the 6. How many are even and greater than 4? Just the 1. So then 2 plus 3 is 5, minus 1 is 4, 6, or 2/3. Questions on that one? Again, or, so we're adding mutually exclusive. You want to make sure you take mutually exclusive. You just add, not mutually exclusive. You want to account for the ones that would be the overlap. All right, now we're talking about a deck of cards. So a card is randomly selected from a standard deck of 52 cards. Find the probability of the given event. Same thing, you want to identify mutually exclusive or not. So selecting a 5 or a face card. Are a 5 and a face card mutually exclusive? Yes. How many 5s, or what's the probability of picking a 5 from your deck of cards? 4 out of 52. How about a face card? 12. And this word says or, which means I'm going to add 12 out of 52. And I could reduce that. They would both be divisible by 2. They're both divisible by 4 even. But if you wanted to add and then reduce, it's totally up to you. So 16 out of 52. 4 over 13. Good. Number 4, selecting a face card or a diamond. Are those mutually exclusive? No. So this time I have to do probability of a face card plus probability of a diamond minus probability of a face card that is a diamond. So what's the probability of a face card? 12 out of 52. A diamond, 13 out of 52. And a face card that is a diamond? Good. 3 out of 52. The jack, the queen, and the king of the diamond. So this is 25 minus 3 is 22 over 52, or 11 over 26. Questions so far? Okay. An ace or a 9? Is an ace and a 9 mutually exclusive? Yes. How many aces? 4 out of 52. A 9. 4 out of 52. 8 out of 52. Or 2 13ths. And the last one, a 10 or a diamond. Mutually exclusive or not? Not. So now it's probability of a 10 plus probability of a diamond minus the probability of the 10 that is the diamond. So there are how many 10s? 4 out of the 52. Diamonds, 13 out of 52. And a 10 that is a diamond, 1 out of 52. 17 minus 1 is 16 out of 52. Again, divisible by 4, so 4 13ths. So all of these were or problems. When we get into independent and that kind of stuff, that's usually when the and comes, which is what we're going to talk about a lot more today. Questions on any of those? So probabilities of independent events. So we talked a little about independent yesterday. And we're going to bring, well, we talked about both, independent, but we're going to bring them back in. We talked about how to find it if they're independent. Now we're going to figure out how to find it if they're dependent. So a complement is one of the ways that you can find, it's almost like the probability, if the probability of what you're looking for is less likely than the probability of what you're not looking for, if that makes sense. So if I was to say, what's the probability, it's kind of easier, but it will get more difficult. The probability of picking a number greater than 3 of a deck of cards. There are a lot of numbers bigger than 3. So it is easier to find the probability of picking under 3 and subtracting it from 1. So that's a complement. The complement is 1 minus the probability of an event. And it only makes sense to do it if the probability of what you're looking for is technically harder to find than the probability of what it wouldn't be. I don't know if that makes sense. We'll do an example. But the little a with the bar over it is literally read as a bar, and that's how you show the complement to something. So if I asked you what the probability of a is and you wanted to find the complement to it, you would do 1 minus the probability of a. So if we were to look at this, and you don't have that little box on the right yet. Oh, you do. Okay, so we're going to pretend like it's not there first, because think about what would happen if I didn't have it, is kind of what you want to do. When 2 6-sided dice are rolled, find the probability of each event. So if I have a 6-sided die, I'm going to actually zoom it this way, and I roll it twice. The first time I could get 1, 2, 3, 4, 5, 6. The second time I get 1, 2, 3, 4, 5, 6. Which means my sample set could be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, or 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, or 3, 1. I could go all the way through, right? Or my sample set would be the number in the first event times the number in the second event, which means how many are in my sample set? There's 36 different options I could get. You with me so far? So if I actually listed them out, they would look like what's on the right here. Okay, they just made a chart from it. So here's what I would roll the first time, here's what I would have rolled the second time, and then in between is their sum. So if I wanted to look at the sum of what's being rolled, that's what's formed there. That chart's probably not going to be given to you if it's a question like that. You'd have to figure it out. However, it's there so that you could start to visualize what we're going to talk about. So it says the sum is not 6. So I know that my set is, so whatever it is, it's going to be over 36. The question is, how many are not 6? So if I looked at my chart, again, this is already given it to you, but if you had literally gone through and done 1 plus 1 and 1 plus 2 and 1 plus 3 and 1 plus 4 and 1 plus 5, that's a lot to figure out how many are not 6. What happens more? That it's not 6 or that it is 6? That it's not 6, right? So in the idea of complements is that it's easier to find what would be 6 and subtract it from 1. So how many of those sums add up to 6? 5 plus 1, 4 plus 2, 3 plus 3, 4 plus 2, 5 plus 1. There are 5 that sum to 6, which means that 1 minus 5 out of the 36, which would be 36 minus 36, 31 over 36, would match how many are not 6. So in a scenario like this, it's easier to find what would be 6 and then just subtract it from 1. That's when you would use the complement.
But assuming we didn't have the chart, we would have to...
It's still going to be easier because think about it. Like if I were to add up those numbers, so that 1, 2, 3, 4, 5, 6, 1, 2, 3.
Yes, but you would still be adding all of those up.
No.
No?
You could either be adding them and find all the ones that are not 6, or you could just find how many are 6.
Right.
That's going to be way faster, right?
Yeah.
Does that make sense? Yeah? Okay. So for B, it says the sum is less than, So this one says the sum is less than or equal to 9. So again, if I was going to go through and find out how many were less than or equal to 9, 1 plus 1 is less than or equal to 9. 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5, 1 plus 6. All of those are less than or equal to 9, right? 2 plus 1, 2 plus 2, 2 plus 3, 2 plus 4, 2 plus 5. All of those are less than or equal to 9. It's going to be more that are less than or equal to 9 than the opposite. So what I can do here is say 1 minus the number that are greater than 9. So greater than 9 would be 6 and 6, 5 and 6, 4 and 6, 3 and 6. And I can work my way backwards. So that's what's already in this chart. So if I'm looking for ones that are greater than 9, it is simply these 6 totals. So instead of adding up all the other ones, I can just do 1 minus those 6 over 36. 1 minus 1 6, which is 6 sixths, minus 1 6, or 5 sixths. So you will never be forced to do, well, not in here, forced to use the complement, and the homework is going to ask you to use it, but on a test it did not put that you had to use the complement. It's one of those things that sometimes it's just faster to use it. So if what you're looking for would take longer to find than the opposite of what you're looking for, then it's going to be quicker to use the complement. All right, so now we're going to go back to independent versus dependent. So yesterday we talked about what are the difference between, well, we talked about independent. We said 2 events are independent if the occurrence of one does not affect the occurrence of the other. So a lot of that is a with replacement scenario, or a randomly generated number, or a flip of a coin, or a roll of a dice. What happens the first time does not impact what happens the second time. So if I ask you to pull a number out of the cup, and you put it back, and then I go to Mikhail, he has the same exact situation. Those are independent events. What happened to you does not impact what happens to him. He has the same set to choose from. But if you pull it out and you keep it, now he has less of a set to pull from. So that's a dependent, right? If you pull a rock out of a bag and you keep it, now whoever's going next has less to pull from. And also what you pulled affects them. So if what I'm pulling is 2 blacks in a row and you take a black out of that bag, now I have 1 less black to pull and my sample set is less. Does that make sense? So you're impacting it in 2 ways. When we originally did with replacement and without replacement, you weren't doing 2 probabilities multiplied together, which is what an and is going to happen. So what's the probability of getting a black and a red, or 2 blacks? If you pull it out of a deck of cards and you keep that card, that's a dependent event, and that's going to change your probability. If you take it and you put it back in, now it's an independent event. You're starting from the same set every time. Does that make sense? Yeah? Okay. So all of these are going to be dealt with and statements. What's the probability of getting this and this? That's multiplication instead of addition. So example 2 says, tell whether the events are independent or dependent. A box contains yellow and brown dog treats. You randomly choose 1 dog treat from the box and you don't replace it. Then you randomly choose another dog treat. Your 2 events are event A, the first dog treat you choose is yellow. Event B, the second dog treat you choose is brown. So is what happening in A affecting B?
No.
Why?
Because they put it back.
You do not replace it.
So it does affect
So it does affect it. So this is dependent. So 1 little word changes the whole thing.
So it's dependent because you did not replace it?
Correct. You altered the set, right? Example 3, same thing. Tell whether it's independent or dependent. A jar contains red and blue marbles. You randomly choose a marble from the jar and then replace it. Then you randomly choose another marble. A is you choose a red marble, and B is you choose a blue marble. Is B reliant upon A? No, why?
Because you did.
Because you replaced it. So this is independent. All right, so conditional probability is exactly what happens as a result of a dependent event. If the probability that event B occurs, given that A has occurred, it's called conditional. And it's written as that. So the probability of B equals the probability of B assuming A has already happened. So not only do you assume, let's say that A is to pick red and B is to pick red again, let's just say. Not only do we assume that they eliminated my sample choice, right? So we reduced whatever the set was down 1. We assume they got what they wanted to get. So not only is it reducing, let's say it's a deck of cards, my card deck just went from 52 to 51, but my reds just went from 26 to 25. So you're assuming this, what this means is the probability that B occurs given A has already occurred. Not that a probability of A has already occurred, but that it actually happened. Does that make sense? Okay. So if they're independent, which is what we talked about yesterday, that first whole block is what we did yesterday, and the question is and. The probability that A happens and the probability that B happens given that they're independent, then to find the and, we multiply the probabilities together. For dependence, we multiply the probability that A happens times the probability that A happens that B happens given A has already happened. So this is when you're dealing with your altered subset. Sometimes they'll ask you for different portions of that exact same statement. So if this is what we just said, if we said that the probability of A and B happening in a dependent scenario is given by the probability of A times the probability of B given A has already happened, then I can solve for any specific part on the right side by just dividing by the other part. So if the question comes up, here's the probability of both A and B happening, and then here's the probability of just A happening. What's the probability of B given A happening? We can simply take that equation and divide by the probability of A, which is what this is, and solve for a different part. For that, I could even solve for the probability of A happening, right? If we said the probability of A and B happening is blank, and the probability of B given A happens is this, what's the probability of A? You could just rearrange that whole formula. And that little line, I don't even know what that is. You could just totally ignore it. I don't know where it came from. Pretend it's not there. All right, so some more examples. You spin the spinner shown, which is divided into 8 equal parts. Find the probability that you get red on your first spin and blue on your second spin. So now you have to ask yourself, is it dependent or independent, and then go from there. So is it independent or dependent? Independent. The spinner doesn't change after you spin, right? On the spinner that I have like the names, if I spin a name, I can choose to take that name out or leave it in. That would be, so if I chose to take it out, now it's dependent. But if it's something like this where the actual spinner doesn't change, okay, then it's independent. So I want to find the probability that you land on red the first time, and, which means multiplication, the probability you land on blue the second time. So what's the probability you land on red?
3 of 8.
There's 3 of them, right? So 3 out of 8. And the probability you land on blue? 2 eighths. So I could reduce this 1/4, and I get 3 out of 32. What would change if that said the probability you get on one spin that you get red or blue? Now you add them. You see the difference? So and is usually 2 events, and the probability is, does this happen and this happen? Or is usually 1 event. What's the probability you're doing this or that? And it's going to be more likely in 1 event that you do an or than it is on 2 events you do an and. All right, a bowl contains 36 green grapes and 14 purple grapes, sorry. You randomly choose a grape, eat it. You don't put it back, FYI, because last year somebody mentioned that you could eat it and put it back. We're not assuming we're dealing with 3-year-olds. They have eaten it and swallowed it. Did not put it back in the bowl. And then randomly choose another grape. Find the probability that both events A and B will occur. Event A is the first grape is green, and event B, the second grape is green. Is this dependent or independent? Dependent. So event A times event B given A has already happened. So how many green grapes are there?
36.
And how many total grapes are there? So if we assume A has happened, that the person not only pulled a grape, but pulled a green grape, then how many green grapes are left for event B? 35. And how many grapes are left in the bowl?
41.
There you go. Does that make sense?
So when you do this, you would see your numerator decrease and your denominator decrease?
if it's the same thing though, because this could have been green grape and then red or purple grape. Now the green grape is 36 out of 50. The purple grape is 14 out of 49. So the top doesn't change what it would have been, but the bottom would change. Does that make sense? Only if it's a repeated thing. So I can reduce this. This is what? No, B given A has happened. The little dash is the given. So this is 5/7. Can you get it? Here. You're welcome. 18. Wait. Oh, yeah, you can cross cancel that way too. Yeah, 5. And that should be 35 here. Yeah. That's a 3. All right, so number 1 says a drawer contains 12 white socks and 8 black socks. You randomly choose one sock and you don't replace it. Then you randomly choose another sock. What's the probability both socks chosen are white? Dependent or independent? Dependent, you don't replace it, right? So if the probability that the first one is white times the probability that the second one is white, given the first one was white. So the first time I go up to pick what's my probability? 12 over 20, right? And then we assume that a white one was chosen the first time, which means my numerator now goes down to what? 11. And the bottom? 19. So we lost a sock. So God bless you. 3/4. 33 over 76. You're assuming what you wanted the first time happened.
Okay. That makes sense.
Wouldn't 3 over 5?
Yeah.
Oh, 3 over 5. Sorry, just kidding.
Yeah, that makes it 95.
Yes, it does.
Does this mean that this one has 2 possible answers, or would it be the same?
No, it's always the same.
So if I used 8 for the first one, and then it would be 8 over 20 multiplied by 7.
Why 8? No. That's if it's a black sock. So you're assuming that they're both white socks.
Yeah, but it doesn't say. Does it say in the problems that they're white? That I'm choosing the white one though?
Yeah, it says, but you're choosing both are white.
Ah.
Yep.
Alright, I can't read.
Just figure out how to read before Wednesday and you're good. Suppose you flip a coin twice. What's the probability that you get tails on the first flip and tails on the second flip? Independent or dependent? Independent. Okay, probability you get tails on the first, so the probability you get tails, and the probability you get tails again. Tails would be 1/2. Tails would be 1/2 again, so this is 1/4. Questions? All right, so this one says the table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and B, the probability that a hurricane is in the northern hemisphere. So we are assuming for A that it's the probability of a future cyclone, which is prediction, right, in the northern hemisphere and a hurricane. So you can go through like all the work of figuring out the ands and like all the little formulas, or you can just use a little bit of common sense when it comes to charts. I'm looking for northern hemisphere and a hurricane. So northern hemisphere means it would be anything in this section, and hurricane is anything in this row. So the two overlap at 545. So 545 is how many of the total amount of storms have happened that are in the northern hemisphere and hurricanes. So all I have to do is take and add those up and divide by the total. So I would say 199 plus 18 plus 398 plus 200 plus 545 plus 215. And then reduce it.
You add all the numbers?
Yep, because it didn't give you anything specific at first. You're pulling from the big set. And that's what the difference between A and B is, which you'll see in a second. 315. If it asks for it, so sometimes standardized tests will ask for it in terms of percent. What's percent of probability? Yep, just divide it. And this would be 0.346, so that would be 34.5%. 34.6%, sorry. B says the probability that a hurricane is in the northern hemisphere. So we're already assuming it's in the northern hemisphere, which means we have taken our sample set of the southern hemisphere out of it. Okay? So we can ignore the southern hemisphere and focus solely on the northern hemisphere, which changes our sample set. Now the bottom is just the 199 plus the 398 plus the 545, which is 1142. And the top is the hurricanes, which is 545. Or 47.7%. Yes.
Where did you get the 1575 from A?
I added up everything on that thing. So you're saying from general, just from looking at these storms, what's the probability that the next one is going to be in the northern hemisphere and be a hurricane? So you're using the entire subset. Whereas B, it says the probability that a hurricane is in the northern hemisphere. You're already assuming it's just the northern hemisphere. But what's the probability that it's going to be a hurricane? Okay, now the last slide, which is just more replacement, non-replacement. So hopefully this is a little bit easier. You randomly select 2 cards from a standard deck of 52 cards. What's the probability that the first card is not a heart and the second is a heart? If A, you replace the first card before selecting the second, and B, do not. So let's go with A first. If you replace it, then it's what? Independent. So I'm going to do the probability that it's not a heart times the probability that it is a heart.
So would we do like the thing where we have to find?
So probably easier to use the complement here, right? It's easier for it. What's an easier one to find? The number of hearts or the number of not hearts? The number of hearts, right? We know the number of hearts is how many? 13 of the 52, or 1/4 of your deck. Yes? So how many are not hearts?
3/4.
3/4.
So you multiply that by 1/4?
Yep, 3/4 by 1/4, which is 3/16. That's if it's not, that's if it is replaced.
3/4 is from not a heart.
Not a heart, yep. So A is independent, just multiply them out. B is saying you don't replace the first card. So we said that 13 of the 52 were hearts, right? Which means if I subtract that, what is that, 39 of the 52 are not hearts. So if the probability that the first card is not a heart
13 over 51.
would be, no, the other way around. The probability that's not a heart is 39 over 52. And then the probability that it is a heart given a non-heart was pulled first. So there's still 13 hearts left because we didn't pull a heart the first time, but there is 51 cards left. Does that make sense? Okay. So this would be 13, 17, 1, 13. Oh, 4. Just kidding.
Why wouldn't it just be 3/4 times 13?
Because you didn't put it back.
What's the first card though?
Oh, it could be 3/4. It's the same thing.
Oh. Okay.
All right, so I told you yesterday, I just want to repeat myself every day that 1 part of your test is calculator, part is not. Larger numbers assume will be, smaller numbers will not be. That's how it will get divided. 2 is you're taking your test, the full test. There's 18 questions on the test. 17 of them you will get on Wednesday, and on Tuesday at the end of class, you will get the expanded binomial one, okay? I put an assignment on your to-do list for Tuesday to remind you. Emily clearly confused that with today. It was next Tuesday. I don't care if you're ready ahead of time as long as you're still ready then, right? You can use your scientific calculator on that question too. So I would make sure that you have it both Tuesday and Wednesday. Don't come on Wednesday and ask me how to use the calculator. There will not be time.